Hi, in this video we'll be talking about binomial coefficients. So before we move into talking about n choose k in specific, let's talk about where they came from. So when we binomially expand the term a plus b to the power n, we get all these terms whose general term can be written as n choose k, a to the power k, b to the power n minus k, right? Now, the coefficient of this a and b in this general term is called binomial coefficients, and it is also known to be n choose k, or the common n choose k notation that we know of, right? So this n choose k is mathematically defined as n factorial divided by n minus k factorial multiplied by k factorial, and sometimes it's also denoted by this particular symbol. Okay, so if we use this particular symbol anywhere after this, just understand that this is nothing but n choose k. Okay, now why do we call this n choose k, or why does this represent actually the choice of k objects from n distinct objects? Okay, so let's take this experiment of having, let's say, 5 objects, okay, and finding out how many ways are there to choose k objects out of it. Now note that these are distinct objects, okay, so they are somehow labeled, okay, and the number of ways in which we can choose any 2 items. So the way this works is this n factorial is actually the number of ways to permute it in all possible orderings. Okay, now let's say we decide on which we always choose the first 2 elements. Okay, let's say k is equal to 2, so we want to choose 2 elements, so we always choose the first 2 elements in this particular permutation. Now if out of all n factorial permutations we take these 2 permutations, that there is a 2 over here, there is a 1 over here, and this remains same. Now this is actually selecting the same set of people, right? So we divide it by this k factorial over here, which means the intra permutation between this group selected, right? Also this intra permutation between the group of non-selected peoples needs to be excluded, and hence we have this n minus k factorial divided as well. So this is how this n choose k actually mean choosing n out of n distinct people, k people, right? Now by this definition we can also understand that this particular relation, that n choose k is equal to n choose n minus k, is also true, because the number of ways to select this particular group is also same as the number of ways to select this particular group, right? So you can either choose the group which is getting selected, or you can choose the group which is not getting selected, which by means of complementation means that whichever element you did not choose will get selected, right? So these two would be the same. Okay, now how do we calculate this n choose k number whenever we needed some particular code? So there are 3 particular methods that are used in different scenarios, so you need to know when to use which one. Okay, so there is a method using factorials, which is the most common one. Okay, then there is a Pascal's triangle method, and then there is a multiplication method. Okay, so we would be talking about each of these in depth. So what is this factorials method? So we know that n choose k is defined as n factorial divided by n minus k factorial multiplied by k factorial, right? So there are a lot of factorials involved. So if we can somehow pre-compute these factorials and just divide n factorial by these 2 values from the array or somewhere where we store the factorials, we can get this value quite fast, right? So factorial method is used in places where n is up to, let's say, 10 to the power 6 or something similar, and the n choose k needs to be found using some prime p, which is for which this exists as, for which the inverses exist for all numbers between 1 to n. Okay, so we need to find for some prime p. Okay, and if it's not prime, the inverses should exist for 1 to n. That should be the general condition. Okay, so generally if it's prime, the inverses exist. Okay, this prime can be pretty large, it can be greater than up to 10 to the power 9. Most common choice is 10 to the power 9 plus 7, right? So this is the most common type of constraint that you will see in problems where you need to calculate n choose k, and this is the method that you would be using in those particular scenario. So what we need to do is we need to calculate an array. We create an array with factorial in it. So we initialize factorial of 0 equal to 1, because number of ways to permute 0 objects is 1, right? That's how factorial is defined. Now we use a recursive relation of factorial of I is equal to factorial of I minus 1, right? So this will define 1 multiplied by 2 multiplied by 3 multiplied by 4 so on up to I minus 1 multiplied by I, right? This is what the definition is, and we need to calculate all of these things in a modulo p, right? So this is given to us in the problem. So this we can do using a loop. So as you can see that we need up to n 10 to the power 6, right? So we have to calculate the factorial up to 10 to the power 6, but that's okay because this is a linear pre-computation that we are doing once. After that, for any n choose k given, what we need to do is we just need to calculate factorial of n multiplied by factorial of n minus r inverse, okay, multiplied by factorial of r inverse, okay. So this is how you calculate n choose r, okay. Now these are just accesses to arrays, so you can get these values pretty fast. Now these inverses you can also pre-compute if you want to, or you can just use a exponentiation technique. So we know that we can, for any prime p, a to the power p minus 2 is actually the inverse of a, right? So we can use that over here and find out these inverses pretty fast. So we can calculate any n choose r once this pre-computation is done in linear time. For every n choose r, this will be order log n. We can even make this order 1 if we want to by just pre-computing this inverses as well, right? So for all the factorials we are saving the factorial values in an array, right? So make an inverse factorial array as well and just save the inverses of all the numbers that you need, right? So with this pre-computation, calculating n choose r repeatedly becomes pretty easy and you can find them in order 1, right? So all of these multiplications also need to be done properly mod p. So make sure you just multiply two terms first and then take a mod p and then multiply the other term and then take a mod p, right? These are some things that needs to be taken care in implementation, but this is the whole idea. Okay, so this is the factorial method and we use them when the n is pretty small, like up to 10 to the power 6, okay, because we need this pre-computation which is order n, right? Now there is another method called Pascal's triangle method. So this is nothing but using the relation that is defined in n choose r triangle. Okay, so this Pascal's triangle is a row wise n choose k put together. So there is a nice property that n choose k follows, that if you, this is nothing but n choose, this is nothing but 0 1 choose 0 1 choose 1, this is 2 choose 0 2 choose 1 2 choose 2, right? So these are the values that I've written over here, and these are nothing but these binomial coefficients. So this is for n equal to 2, n equal to 1, n equal to 0 and so on, right? These are all these values of binomial coefficients only. Now there is a nice property that this follows, is any particular value is sum of its two numbers that are in the previous row, right? So we sometimes also write it in a skewed form, something like this: 1 1 1 1 2 1. So this will be sum of these two values, right? So for this we can use a simple relation n choose r of sum n and r is equal to, so this is like an array we are talking about, 2D array, okay, n choose r of n minus 1. So for this n choose r we are going one step up, n choose r plus n choose r n minus 1 r minus 1, right? So this is followed in the n choose r relations. So we know this particular relation, that n minus 1 choose r plus n minus 1 choose r minus 1 is equal to n choose r, right? This holds true using this Pascal's triangle. Okay, now this particular relation can be used to create a 2D table. Okay, so we can just simply create this 2D table that we are seeing over here, and we can then just answer the value for any n and r from this like array that we are computing. Note that when you are computing this particular array, this particular r might become negative if you are not handling them correctly. So make sure that whenever r is equal to 0, you make them trivially 1, because whenever r is 0, we know that the n choose r is always 1, right? So that can be handled separately, but this is the whole relation that we will be using to build the array. Okay, now when to use this particular method? So let's say in a particular question you are given n is less than equal to 4000 or something like that, okay, so that you can do this computation will take you order n square, right, because this is a 2D table that we are filling, and we will have to fill this for from 1 to all n to n, then only this. So every level is using its previous level's value, so we will have to fill this for all the values up to nth row, and that too will take, like, there are in total order n square number of entries over here, right? So this would take order n square. So if the constraints are up to this, we can use this. But the good thing about this, why don't we always use the previous method, is this method works with any prime. Okay, this method works with any prime, and not just prime, you can use any composite number as well. Now why is that? Now note that n choose r is defined even if, like, the modulo that you are taking in the problem is not prime, right? So n choose r is a number and you should get a result, right? But you cannot use this previous method in case the p or the modulo that you need to take in the problem is not prime. Why? Because you need to calculate these inverses, and inverses exist only when this is prime or there is some special property followed, right? So you can use this particular relation that a to the power p minus 2 is the inverse of a only when p is prime. So this method can be used even when, let's say, we are taking everything modulo p, but p is not prime, because the only operation that we are doing over here is addition, right? And we know that modulo can easily handle addition even if it's not prime, right? So in case the modulo in the problem is not prime, then you need to use this Pascal's triangle method to calculate this, okay? Now let's talk about the last method, that is multiplication method. Now this is just using the formula n plus n factorial divided by n minus r factorial, right? This, we will be using this particular formula. And so in this thing, whenever you are given some particular problem, let's say n is up to 10 to the power 18, okay, but either r is less than equal to some small number 20 or some finite size up to 10 to the power 6, let's say r is up to 10 to the power 6, okay, or let's say n minus r is up to 10 to the power 6. So in these two cases you can compute one n choose r using this particular method. So if you need repeated n choose r's, then the question will give you some constraint like n is less than equal to 20, but let's just assume that we just need to calculate n choose r only once, and let's say n is up to 10 to the power 18 and you need to find this, and let's suppose the modulo given is prime, okay, is prime, okay. So how do we do that in this case? So even if n is pretty large, r is small, right? So what will happen is this particular part over here, so there would be 10 to the power 6 terms over here, and there would be 10 to the power up to 18 minus 10 to the power 6 number of terms over here, right? So now we know that we can cancel off terms in factorials, right? So we can write this particular thing, let's talk about this. So we can write this particular thing in this form, that summation over n plus, or let's say n minus I divided by I plus 1, I equal to 0 to r. We can write this thing in this particular format as well. Now this is nothing but cancelling this n minus r factorial with everything in the top, and the rest of the terms would be of this form and this would be here, okay. Now we just need to calculate this particular summation, and note that this summation is only up to r. So in case this r is small, then we can run this loop and calculate this particular term, right? So this is nothing, this is not summation, in fact this would be product, right? This would be product, okay. So product of n minus I divided by I plus 1, right? So these are the top terms which are not cancelled by this n minus r term, and this is the r factorial expanded, right? So now we just loop for r times and then like keep on multiplying on the top, taking modulo properly, and then taking the inverse of the denominator and multiplying it to the top. That's it. So that will compute this in order r, in fact order r log of p, because inverse takes order p, order log p, because we would be doing a to the power p minus 2, and that is log of the power, right? So this would be order log p. right? So we can calculate n choose r in r log p. Also, in case this is smaller and r is large, what we can use is the relation that we talked about, that n choose r is equal to n choose r minus 1, r n minus r, right? This is a relation that is followed. So we can just flip the values if you want to and make the denominator, make the r smaller. Like if r is large but n minus r is small, you can just flip the value, right? You can calculate this instead of n minus r, right? And that would be small. Okay. So this is the multiplication method, which is helpful in case like one of the terms is small, like either r is small or n minus r is small, right? So each of the method has its own benefit, and this allows you to calculate even like n choose r for some special cases of n being pretty large. Okay. Now let's talk about some relations that are frequently used in competitive programming using binomial coefficients. The first one being n choose I summation over I equal to 0 to n to be equal to n 2 to the power n. Now how does this hold true? This is nothing but having the binomial expansion of 1 plus x. Okay, this will be nothing but n choose 0 plus n choose 1 x plus n choose 2 x square and so on, right? This would be the terms. So what if in this relation we put x equals to 1, we get n choose 0 plus n choose 1 plus n choose 2 in the right hand side, so on, and in the left hand side we get 2 to the power n, right? So with this binomial expansion theorem, you can prove this particular relation to be true. Derivative of this particular relation is this as well. So this is like a modification done to this particular expression. So what we do is we just differentiate this and then put x equals to 1 to get this particular relation. Okay. So similarly, if you have something like I square, n choose I and all, you can also keep on differentiating this expression. Like you differentiate, multiply with x and then again differentiate and so on. You can keep doing that and you will get the any particular I to the power k n choose I particular term. Okay. So this would be needing some differentiation, but we would not be going into that for this particular video. We'd be restricting us to this particular relation. Okay. So these are the two relations which we get from substituting x values in binomial coefficient. Let's look at the next one. So m choose k summation from m equal to k to n. So that means this top part of n choose k is increasing, right? Now this turns out to be equal to n plus 1 choose k plus 1, and this formula is famously called hockey stick formula. Now why is this the case? Let's first understand why is this called hockey stick. So let's take a case. So let's say n is equal to 4 and k is equal to 1. That means we are talking about one choose 1 plus 2 choose 1 plus 3 choose 1 plus 4 choose 1, right? And this would come out to be 10, right? This would be 1 2 3 4 and 10, right? Now why is this called hockey stick formula? Because if you talk about where is this 1 choose 1, 2 choose 1 and all, these are these things over here, and the answer for this is always this particular number. Okay, the answer for this is always this particular number. So this looks like a hockey stick, and that's why this is called hockey stick formula. Okay. Now you can also think about this combinatorially. So this would be like, let's say there are n plus 1 people and you need to choose k plus 1 people out of it. So what we can do is either we say that the last person chosen is n plus 1th person. So in that case, out of n people you will have to choose k people, or else if the last person taken is not n plus 1th person, then you look for like the smaller value. So you now need to say that, okay, let's say the second last value is the chosen person, is the k plus 1th person. So in that case it should be n minus 1 choose k and so on, right? So that formula would come out to be. So that's just an intuitive idea for how this left hand side and right hand side are equal. Okay, so in case you forgot about that, you can think in this intuition, or also you can talk about this Pascal's triangle representation of this hockey stick, right? That's quite easy to remember. Now let's look at one more relation that is called Vandermont's identity, which is nothing but n choose I multiplied by m choose k minus I summation over I equal to 0 to k. Okay, this comes out to be n plus m choose k. Now this is pretty easy to like understand why the left hand side is equal to right hand side, because let's say there is a group of people with n plus m size, okay, and you need to choose k people as the representative. So and we say that let's suppose n of them are male and m of them are female. So this k can come from any of the group, right, out of male or female, right? So we just enumerate that possible choice over here, that okay, out of n, let's say we choose I, and from m we choose k minus I, and we add that up for all k's, all I equal to 0 to k. That gives us this whole choice, right? Because it's just random selection between from n plus m people, and you need to choose k representative, right? So this is a intuitive way to think about this particular relation. Okay, now this is quite frequently used in mathematical based or combinatorial based problems in number theory. So keep this formula in mind. Okay, this, if one of them is like, if the top part is same and one of them is increasing and the other one is decreasing, it might be a Watermont entity. Okay, now a special case of this Watermont entity would be this particular relation, that what is n choose I squares summation from 0 to n. Now this can be easily found out to be 2n choose n, because if you put k equal to n and m equal to n, this is nothing but this particular relation, right? And then this would be just this right hand side. This, if you put n and n over here, this is 2n choose n, right? So this is a special case of this. Okay, now let's talk about this particular expression. This is one of the most frequently used expression in mathematical part of competitive programming. So given an expression of x1 plus x2 plus x3 so on up to xn, which is equal to some value r, find out the number of solutions of this particular expression, where each of the individual variables can be from 0 to r. Okay, now the number of solutions for this comes out to be this particular relation, that n, the number of variables plus the sum, this r would be capital R. I hope you got the point. This r is this particular thing, and subtracted by 1, choose n minus 1, right? Now how does this come out to this particular number? So we would be like quickly looking at one particular intuitive idea for this correlation. So it's nothing but, let's say r is equal to 5 and n is equal to 3. So what we are doing is we are drawing 5 plus 2, 7 number of dots, okay, n plus r minus 1 dots, and we will choose n minus 1 dots. That means number of variables minus 1 choices. So what we are basically doing is, if we choose, let's say this and this, that basically means that the first variable gets 2, the second variable gets 1, the third variable gets 2. So if you, based on where you choose these two breakpoints, like n minus 1 breakpoints, the values of the variables will get assigned. So there is a one-to-one correspondence between this problem and this particular expression over here, right? And this is famously called bar and stick formula. So you just place the bar over here, right? Okay, so you don't need to like every time think about this like intuitive idea. You can just keep this particular formula in mind as well, because this is frequently used and you will need to use this in a lot of problems. Okay, now let's talk about one more expression. So this is, the numerator is decreasing and the denominator is increasing. Okay, so you start from n, choose 0, then n minus 1 choose 1, n minus 2 choose 2, and so on. This turns out to be equal to Fibonacci of n plus 1. Okay, now why is this particular thing holding up is you can prove this separately. Like this is you can use an inductive proof if you want to. However, we'd be not discussing this particular idea over here, because this is a very, like, this would take a lot of time to prove this particular expression. Now if you think about what this actually can mean, this actually means that if you sum up the diagonals, right, in the Pascal's triangle, this particular summation over here means the sum of this diagonal, right? Now this diagonal sum in Pascal's triangles comes out to be the Fibonacci values. Okay, and this is a nice observation. This particular relation is not used frequently, like this is a very rare expression, but however, if sometime a question comes up on this particular summation, you might be able to directly find out that okay, that's nothing but Fibonacci of n plus 1, right? Okay, now let's talk about one theorem that n choose m follows, or n choose r follows. So whenever you need to calculate n choose m, mod p for a large n and a small prime p. Okay, let's say this is the scenario. Make sense? So in this particular scenario, you can use something called Lucas theorem, which says that, okay, write n in base p, write m in base p, and take corresponding chooses and multiply them mod p. Now let me explain it using a recursive definition over here. So what you can do is you can take n and take a modulo p, you can take m and take a modulo p, and then you find out this particular choose and then divide n by p and m by p, and then recursively calculate this using this Lucas theorem again. So if this is still large, then you again apply this particular theorem. So you can make this again n by p, you can take this to n by p square, and there will be another modulo term. So there will be a lot of n mod p, m mod p multiplied in sequences, and that would be the final value taken after multiplication. You need to take just a mod p. So if you think about this, this is nothing but like writing n in, let's say, n1, n2, n3, n4 in base p. Okay, so you represent n in base p. Similarly, you represent m in base p. Okay, so this is the highest, this is most significant bit, and this is the least significant bit. Okay, so let's suppose this is the case. In case like the m is smaller, we can always prepend with zeros, right? And then just take corresponding chooses and multiply them and take a mod p. This would be your final value of n choose m mod p. Okay, so this is called Lucas theorem. We will not be definitely going into the proof because this is very complicated. However, this theorem sometimes helps us when in case n is pretty large or m is pretty large and p is prime. Okay, so I think that's all on n choose r. We'll be taking up another topic on mathematics in the next video.